One of my favorite applications in KSP is talking about the common ion effect. Now, we saw a lot of the common ion effect in our introductory chapter to equilibrium with respect to Le Chatelier. So it's kind of time to talk about that just one more time. Now, Le Chatelier says that essentially when a system is in equilibrium, it will tend to move away from sources of stress. We would call that a dynamic system. It will respond to the sources of stress. Just like us, a system will tend to try and reduce sources of stress. One of those sources of stress can be an increase in concentration or a decrease in concentration of a common ion. So, for example, if we had something like AgCl, and it commonly would split up into Ag and Cl. Now remember that that isn't technically an insoluble compound, so this only does this to a small extent, less than 1/10,000th molar. We could add into that solution something like HCl, which is highly aqueous. Now we do know that when HCl likes to go into water that it will dissociate into H and Cl. But notice that both equations have something in common. They both have that chloride ion. We call this a common ion. They have an ion in common. Now the HCl can't help itself. 100% of it is going to dissociate into H1 plus and Cl1 minus. So it will in effect ramp up the concentration of chloride ions to whatever it can make. And because of that, it actually is going to create a source of stress for the AgCl and tends to push its equilibrium back toward the reactant side. In this case, we would actually see a precipitate forming. Now, although that's all well and good qualitatively, it's important that we see this quantitatively. So let's actually put some numbers to this. So let's calculate the molar solubility of barium sulfate in two ways. First of all, let's calculate it in pure water, and then let's also calculate it in a solution that already contains a 0.010 molar solution of sodium sulfate. So again, let's first start with what we know. We know that we're going to be dealing with a KSP calculation, and it's important that we start off by looking at an equation. So let's look at the dissociation equation for the barium sulfate. BaSO4, double-headed arrow is going to fall apart into Ba2 plus and SO4 2 minus ions. Let's also define the equilibrium expression, KSP. That's going to equal the concentration of the barium times the concentration of the sulfate. And in like manner, let's start plugging in numbers that we do know. We know the KSP number is 1.1 times 10 to the negative 10th, so we can go ahead and plug that in. And again, we are going to only start by considering this in pure water. So I'm going to ignore for the time being the 0.010 molar sodium sulfate. That's going to come in the second half of this problem. Well, it looks like it's just essentially the same type of problem that we did before. We are given a KSP value, and we're asked to calculate backwards toward a molar solubility. I'm going to go ahead and define that as X, and therefore I'll also know what my barium and my sulfate concentrations are as a function of that molar solubility. Both of them here are going to be defined as X because of the 1-to-1 molar ratios. I'm going to go ahead and plug and chug those values in and simply solve. We find that X equals 1.0 times 10 to the negative fifth. Now again, remember that those actually equal the concentrations of both the barium and the sulfate, but because they are equal to X, that also equals the molar solubility of barium sulfate in pure water. Now I'm just going to kind of tuck that value down toward the bottom of the screen so that we don't forget it. That was the result from the first half of the problem, the molar solubility in pure water. Now I'd like to compare that now by this common ion effect. Now we notice we're going to be adding in a 0.010 molar solution of sodium sulfate. And in fact, they do have a common ion. If we actually put the sodium sulfate into water, it is aqueous and can't help itself. It is very soluble. It will fall apart into sodium and into sulfate. And I have numbers for this, so I want to put those numbers in there. I know that it's 0.010 molar, and through stoichiometry, I therefore know that my sodium concentration is 0.020 molar, and my sulfate concentration is 0.010 molar. And again, I have a common ion. Now, it is absolutely safe to assume here that the amount of sulfate that you're going to get from 100% of the sodium sulfate dissolving is going to be way more than the amount of sulfate that you get from the very tiny amount of barium sulfate that falls apart. So it is safe to assume that 100% of the sulfate in the solution is actually coming from the sodium sulfate, not the barium sulfate. Now, yes, a little bit of it is coming from the barium sulfate, but according to significant figures, it's not a statistically significant enough amount to even worry about mathematically. Now, what that's going to enable me to do then is essentially take the number for that sulfate and just simply plug and chug it in. So as before, we would have defined these values for barium and for sulfate as X. We now actually have a number for that sulfate. That sulfate number is now actually going to be 0.010. And again, that's because 100% of my sodium sulfate is dissolving, and now I know that concentration. So now it's just a matter of plug and chug slightly differently into the problem. KSP equals the barium concentration times the sulfate concentration, but now I know 2 out of 3 of those numbers. I know both KSP as 1.1 times 10 to the negative 10th, and I know the sulfate number is 0.010 molar. Now all I have to do is solve for X, which represents both barium and the barium sulfate. I find that that number equals 1.1 times 10 to the negative 8th. So the molar solubility in 0.01 molar sodium sulfate actually comes out to be 1.1 times 10 to the negative 8th molar. So what we find is that the molar solubility is actually reduced by this common ion. And I'm hoping that that makes sense. Because I increased the concentration of sulfate, this dynamic equilibrium had to respond to that stress. It actually pushed equilibrium further back to the reactant side, creating more precipitate, less material dissolving. And it does make sense, hopefully, that the molarity is now decreased overall in that solution.